Right, and so the second talk in the session is going to be by Giuseppe Castagna, talking about typing records, maps, and structs.
The microphone. Okay, I cannot get you. Okay. Okay, so this is a talk on records again, so which are, as you know, finite maps from labels, keys, attribute names, you name it, to values. Okay, and I will focus on two particular usages of records. One, it is like structs, which means you have a predefined set of labels and mapped into values of different types. And if you select a label that is absent, then you have an error runtime. And the other is dictionary maps, associated tables, in which labels are generated at runtime. And if you select a label that is absent, it gives you one particular value. Nil, null, something. And I will show you how to type a language in which records mix both usages, and also you have a union, intersection, and negation types, and we have a very strong motivation for that. And the problem I will show you how to solve is how to define the subtyping relation and how to type operational records. In the paper, there is also some work on mutable records, but I will not present it here. So record, I don't know how many knows that they were first defined by Tony Hoare in '65 and rapidly adopted by Simula '67 to yield the concept of object and classes. And since then, they were used in a lot of different scenarios. And in particular, as I said, I will focus on two particular usages. The one of structured data, the original proposed by Hoare, and the one of maps, associative arrays, dictionary hashes, lookup tables. Okay? So there are differences between these two, and a lot of difference. And for each difference, you will find a language for which there is an exception on this one. And I want to focus on three aspects. The first one is that for maps, all keys usually have the same type, and they map into values of the same type, while for struct, the different keys can map to different types. Then in the maps, the key are values because you can compute them and use the result to select something in the map. While in struct, they are not necessarily value, and the access is by nominal keys. And also the important part is that accessing a key that is absent in a map gives you nil null, while accessing a key in a struct gives you an error. So to do this thing, I defined a calculus, a functional calculus, in which I added a record, of course, and three operations: selection, deletion, and record concatenation with priority on the right-hand side. And these are the struct operation, if you want. And then I added the map operations, which are, well, the same operation: access, deletion, and concatenation of a single field. But the important thing here is that the label used for this operation can be the result of an expression. And of course, the other difference is that in the rewriting semantics, if you try to select a label that is absent here, the semantics is undefined, while for the map selection, it just gives you nil. Okay? So types, what are the requirements? Well, we want a type system which types cover both map and struct usage and the mixed one. And also we want union, intersection, negation types, very simply because this work stemmed from a collaboration with the developer of Elixir ballerina languages, in which they have these types and also this kind of usage for records. So for example, I will show you the example in Elixir. In Elixir, you have this kind of type in which you have a record that maps the atom foo to atom. In Elixir, atom is just a user-defined constant with a colon before. You have an optional field bar that is mapped to atom, which means if a field for bar is present, then it is mapped to an atom. And any other atom that is neither bar or foo must be mapped into integer if present. Okay? And this is an example of mixed usage because the first two are typical of structs. The third one is typical of maps. For what concerns union and intersection negation type, just show union. With this type here is the type of records that have exactly two fields. One field output, and according to the value of the field, if it is okay, you have a second field socket of type socket. If the output field is error, then you have a second message field whose value is either timeout or a pair delay integer. And notice here that we use or is the union for union type for Elixir. And let me continue this example. So imagine that now you have a record, a map in Elixir parlance of the previous type. If now I do m.foo, I know that where m has this type, I know that foo must be present, so this expression type atom. If I try to do m.bar, since the field is optional, it may be absent, so it is an error at run static type, sorry. But of course, I can use the map selection, and I know that if bar is present, I will receive an atom, otherwise I will get nil. So the expression is type atom union nil. And if I try to select an atom that is neither foo nor bar, then it is the third case that applies, so the system will deduce integer or nil. And finally, the interest of this expression here is that you can put here an expression, not just a key. So let's us put m.foo, this as type atom, so we know that all these cases apply, so it can be an atom, it can be an integer, or if the result of m.foo gives a field that is absent, nil. And finally, if I give an expression that cannot produce any atom, then the system will tell me, oh, this is well typed with type nil, but give me a warning because a selection that always gives nil maybe is not very useful. Okay, so how I did this, I defined some types, which are, there are type constructors like int, bool, atom, arrows, etc. Then we have set theoretic types, union, intersection, negation, the top type that types all the values, and the empty type that types no value. And of course, there are records, which are sets of fields, where fields are of two kinds here. So this is the field that must be present, it's mandatory, and must be associated to a value of type t. And this is the optional field, which means that if a field for L is present, then it must be mapped to something of type t. And this is the usage of struct types. And for map types, we add a new field, which maps some key types, a subset of keys, to some type t, okay? And what is this key types? Well, at least underscore, which means and all the other keys are mapped to value of this type, and something else that depends on the language you use. For example, if you use a language like Ballerina, you have that all the keys are string, and but the map has just defined that you can map a key, a string into integer, so it maps all the strings. You cannot differentiate which strings. So it has just underscore. TypeScript, you can define, of course, underscore, but you can say you map string into something, number into something, and symbol. And the most generic usage is Erlang type spec, where for key types, you can specify any type. So you can define a map that maps functions of type Boolean to integer into something else, even though I think it's not a very good idea. With these types, we can encode already a few things. We can encode open record types, which are which is the types that has the field plus any other field, that is, any other key. If it is present, then it is a type. And we can encode the closed record type, which is the records that have exactly only these fields, since here it says that any other fields, if it's present, it must be associated to a value of the empty type, so it must be absent. And the top type, that is the top record type, which is every record is smaller than this, is just the open record with no other field. The Elixir example I showed you before, here is encoded by this type that says foo is mandatory to atom, bar is optional to atom, any other atom is mapped to int, and everything is else is mapped to 0, because in Elixir, record types are closed, okay? And if you want to write an open record type in Elixir, you write ... here, and so you put a 1 here. Okay, the type system, there are standard rules, one rule for each constructor. For records, just say that this record expression has the closest record expression of the corresponding types. And then you have rules for the struct, rules for the maps. I don't want to comment all of them, just the rules for selection. And notice that for struct selection, if I try to select the label L for E, all it requires is that E is a record in which L is present, and then there may be some other fields. While for map selection, I select the label result of E2 from E1, so we require that E2 is just a record, okay, nothing else, and E2 must be a subset of the labels. And in that case, what I obtain as a result is exactly the same operation applied to the types. So to define this type system, I need to do two things. One is to define the subtyping relation I used here, 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 here. And the other one is to define and compute the type operator I used here, 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 and here. So how do I proceed? Well, for subtyping, I will show you that our record values are particular functions that are called the quasi-constant function. I interpret types as set of values, and therefore I interpret record types as set of quasi-constant functions. Then I define subtyping as one type is smaller than the other if the set of the value of one is smaller than the set of the value of the other. So in particular, I can use this interpretation to decide how to decide, to define how to decide the record subtyping, and I will derive a backtracking-free algorithm. For type operator, the problem is that we can select, do an operation like .l on a type T, which is not just a record type, but it can be a union of intersection of record types and negation of record types. And negation is really what makes things difficult. So what I do is to define a new notation for records in which I embed the negation, and which has the property that any subtype of the open record is a union of this record. And then it is easy to define the operation on these unions. So let me show first the case for Ballerina. In Ballerina, what we have is that you have just, for maps, you can just define a default behavior that means all the other keys are mapped there. And then I define a quasi-constant function, which is just a function which is constant apart from a finite set of its domain. So consider this function f. This is always constant y0 apart from x1, xn. So I call domain of f this x1, xn, and the default value of f the y0. Okay. Once I define this, it's clear that the record value is a quasi-constant function from labels to value or undefined. And a record value is a function that is always undefined apart from a finite set of labels. Well, also a record type is a quasi-constant function, but it's less interesting. What is interesting is that now we know how to interpret the record type. which is the set of all quasi-constant functions from labels to value or undefined, such that their default value is undefined, and the corresponding value are in the corresponding type of the record. Okay, so now we can use this interpretation to decide subtyping. First observation, deciding subtyping is equivalent to decide emptiness of a type, because T1 is smaller than T2 if and only if T1 intersection not T2 is empty. Second thing, every type which is smaller than the open record, it can be put in a disjunctive normal form. That is a union of intersection of records and negation of records. So we have to decide the emptiness of this union. Therefore, we have to decide the emptiness of each term in there. So to do that, we can do it with an unreadable formula that I don't want you to read, okay? The only things that I want, it is in the paper, there is the explanation. The only things that I want you to observe is that this subtyping of these records is defined by decomposing the problem on the subcomponents, so on the default value of these records and on the type of the field of these records. And the second thing is that here we have a NOR, so a naive implementation of this decomposition would be, well, I first try this, if it fails, then I throw away all the hypotheses I added, especially if I add recursive types, and then I start again. So the last point is how to define a backtracking-free subtyping algorithm. So how to decide this without backtracking? Well, first observation, an intersection of records is always the record of intersection. They are like products in that. So I move the intersection inside here, yielding some R0. So now what I have to do is to compute emptiness of these things, and this is equivalent to, again, an unreadable formula. So that checks this is empty if and only if R0 is empty, or I call this phi function, which is defined, which has as parameter the positive one, the set of negative records, and if the set is empty, it is false. If it is not, I pick one R, I do some test, and I do recursive call. So no backtracking there. Okay, type operators. What do I have to do? Well, type operators, if I have just a single record there, it's very easy, okay? So the dot L on a record R is, well, the mapping of R as a function, okay? Provided that this field L is neither undefined nor optional, which means RL doesn't contain undefined in it. For the map selection, well, it's the same. I just do the union of all the labels that are there inside. And if there is the undefined, I remove it and put nil instead. The problem is how to do when now I have to do dot L on a disjunctive normal form of the records. And for doing that, what I do, the problem is the negation. So I embed the negation in my representation here. Again, this thing is that I don't want you to read it, but just notice that this part is composed by a normal record part, this is the labels and this is the default value, plus a set of types that represent the negative part. And the property of this representation is that every type that is a subtype of the open record is equivalent to a union of these records. The second thing is that there is a effective transformation that allows you to map a disjunctive normal form into this union, and the type operators are defined for this new form exactly as on the old form. Okay, so now to define our operation on something that is a subtype of the record, open record, I just transform it into a union, and then I distribute the operation on the unions. The general case is Erlang maps, so very difficult case in which you can map anything into any type. And the problem here is when you have overlapping domains. That is to say, let me give again an example in Elixir. So this is a map that maps a pair of integer term into atom and pair of term integer into integer, where term is the top type in Elixir. And this is semantically equivalent to the record, which maps integer and not integer to atom, not integer and integer into integer, and maps pairs of integers into the empty types. So they must be undefined. And there are different solutions for that. Luau, what it does, it says, yeah, so let's consider it. So we know that all fields of type integer must be undefined because they map to the empty type. TypeScript does a different solution. That is, they restrict the key types just to avoid overlapping. The types they give, they do not overlap. So the solution we chose for Elixir is like TypeScript. We use a fixed set of key types that do not overlap, but a little bit more. So atom, string, etc. Pairs and records. So this is less expressive because you cannot say my map maps from integer string into string, but just from pairs into string. But the advantage is a simple extension of the previous theory. It can be extended with row polymorphism, and other solution is possible as long as your key types do not overlap. So an example in Elixir, you see here I added these two examples that maps map into lists and triples into functions. So why it is an extension of previous theory? Well, the only difference is that the default value now is not a type, but becomes a product indexed on all the key types. This subtyping relation, this is how it was defined before. And the only things that you have to modify now for this case is just this red part. That is, you check the default value for all the key types. And finally, for type operators, you have just slightly to change the representation here. Instead of having a single default type and a set of types, what you have is a tuple of types and a set of tuples where each component corresponds to one different result type. And it has a meaning that you can see in the paper. So conclusion, what I did, it's a type system for mixed usage of struct maps. It is difficult because of the presence of saturated type, especially because of negation. But actually, it boils down to do two things, and that's what the paper does: define and decide subtyping, and define and compute the type operators. So I gave algorithm to decide, compute them, and prove their soundness. So the paper is rather technical, which is a euphemism for boring. I apologize to the reviewers of ICFP, but it has very practical motivation since it's being implemented in Elixir and under consideration for the implementation in Ballerina. Future work, well, row polymorphism, we are quite advanced on that. It's not easy, of course, because union, intersection, negation types. And the other part is we don't want to use in Elixir a fixed set of key types. We would like the programmer to give us the way you partition key types, and so we are working on that. And then I will be happy to have you, to answer your questions if I can. Thank you.
So again, names and affiliations, please.
Sam?
It's on? Is this on? Okay. So fantastic work as always. Sam Tobin-Hochstadt, Indiana University. So one thing that people do in TypeScript is, or in JavaScript generally, is they treat particular symbols as if they were like a named field. And that's in fact what the symbol feature in JavaScript was created for, so you could have something that was both first class but also sort of more like dot rather than indexing. And I wonder, would that be it feels like that ought to be a straightforward extension here, but I'm not certain.
I'm not sure I understand your question.
Okay, well then
so
maybe...
You said in TypeScript, well, what I know in TypeScript...
I don't think they support this in TypeScript today, but this is sort of what you would want.
There is on related work an explanation of how it relates to TypeScript. In TypeScript, you can have one exception, just one case in which you say, no, that's not TypeScript, it's Flow, sorry. In TypeScript, you can have the underscore, string, number, something else, and a finite union of constants. That's all they have, I guess.
Right. TypeScript definitely doesn't handle what I'm asking about. But maybe we should take this offline.
Yeah, and they have the possibility, they put in square brackets, say, but in the square brackets, you can just put string, integer, or things like that.
Yeah.
So,
yeah, sure. But let's take this offline. I think it'll require more explanation.
All right, so I have a question then. Well, A, thanks for the shout out. And B, one of the decisions that we made was like... sorry. Okay. One of the decisions that we made was to restrict the places that type negation was needed. And it seems like quite a lot of the hoops you're having to jump through here are about dealing with negation of record types. And you've already got like a notion of a key type. So do you actually, in this development, need negation on anything other than key types?
I don't think so, because usually if you take the key types and you do the negation, what you are negating, at least in this framework, is all the other labels that you use. So it is a finite, it's a finite set of labels. So intuitively, you can just specify the type of these things. So if you want to say it maps string into something apart from this string, then you just say maps every string there, and this string is mapped into top optional. And so you don't need negation, but well, maybe yes, this is the answer I can give you now, thinking rapidly. But cool. by the way, Luau is, I look at TypeScript, so etc. Luau is really the one that does it the right way.
So, thank you. All right, and on that great note, I think we should thank the speaker.